Ah, okay. What can I do for you?
Can we do a question like the third one on the exam?
Like the third one on the
Where
exam?
it's like the no slip, there's the two discs, or can we just like redo that one?
Yeah, let's redo that one.
That's a great. It's the only one I'm thinking about.
Have you looked at this solution guide?
Yes, I have, but I didn't like go through and redo it yet.
Okay. Okay, so this is problem 3 from exam 2. All right, disc A has a weight of 5 pounds. You know what? I'm going to go ahead and do my known while I read this. All right, weight of A is 5 pounds, which means mass of A is 5 over 32.2 slug. Disc B has a weight of 10 pounds. Mass B equals 10 over 32.2 slug. If no slipping occurs between them, determine the couple moment m, which must be applied to disk A to give it an angular acceleration of 4 radians per second squared. So of A equals 4 radians per second squared. And it's asking us to find m. Okay, so let's just analyze what's going on here for a second. So there's basically something at A that is causing it to spin. It's providing some torque, this M value. So it's like a motor is stuck on A. B is just chilling. B is just sitting there, right? However, because it's like meshed with A, it's providing some resistance to A rotating the way that it wants to. Okay, so a lot of people thought that no slip meant no friction, and that's not the case. There's absolutely friction between the two, and there are normal forces between the two. Okay, both of these forces are equal and opposite of each other. So whatever friction is happening to A because B is attached to it, that same amount is happening in the opposite direction to B. Same with the normal. The normal that is pushing into A because A is snuggled up to it is pushing into B because A is snuggled up to it. Okay, so the forces from one body are absolutely interacting with the motion of another body. All right, so it's that fact, the fact that these two things are meshed with each other, that makes me think when I draw my free body diagram, I should probably go ahead and draw the free body diagram of both of these bodies. Okay, because their motions are coupled in some way. All right, so let's do free body diagrams. So I've got A over here and B over here. We're sitting on pins, so I've gotten, well, I should give myself some coordinates first, X and Y. X and Y. I've got some reactions at these pins. I've got some couple M. And I've got some mass Mg, or better yet, MAG. Right. And then I also need to account for the fact that B is on it. Okay. So let's estimate that the contact point is about right here. It seems to be slightly up and to the right of the pin. So I'm going to have a normal force that pushes against A. Some people got confused about whether that normal force goes into or out of the circle, but it's impossible for a contact force to pull on a surface. It has to push on a surface. So it's going to go push into A. And this is our normal. And then our friction, we can think fairly carefully about the friction and actually intuitively find the correct direction. So A is the one that's driving movement. It's going to move because of this couple. So it's wanting this particle at this contact point to be moving in this direction. And the friction caused by the contact with B is going to oppose that motion. So friction needs to point in the opposite direction at our contact point. So this will be my force of friction here. Okay, I'm gonna move this over just a little bit to give myself room. Right, and then B, we have very, very, very similar things going on. I've got an M, B, G. I've got a B, X, B, Y. And then its contact is just ever so slightly down to the left from the pin. And now that we've figured out the correct directions for A, we just know that they're equal and opposite on B. So normal pushes into B, and the friction, instead of going up and to the left, it goes down and to the right. And in fact, if you notice, the only thing that could possibly cause movement of B, or cause specifically rotation of B, the only thing that can cause that rotation is the force of friction, right? So that friction is legitimately causing the movement of B. And this makes sense if we think about the direction that A is wanting to spin. These two things are going to spin this way, kind of like egg beaters relative to each other. So if we wanted to think about the direction that I expect this to spin, it will be something like that. Okay. So now we've got free body diagrams of both disk A and disk B. And then the next question is, okay, what equations do I think are going to be useful? So when you're looking at this problem, I know we've recently covered impulse momentum. A while back, we did work energy, and a while back further, we did equations of motion for rigid bodies, which these are because they're both rotating and they have volume. They have the opportunity to rotate and translate, but neither of these objects are going to translate because they're both pinned. So which of those three methods do you think are best? Leia?
Oh, I had a question.
Yeah, go ahead.
For the friction force,
Mhm.
for B,
Mm-hmm.
is it in the same direction that the disc is moving?
Yeah.
Okay,
Because it's causing that motion,
okay,
right? It's pushing it. It's the only thing that's pushing it. I mean, we've got all of these other forces, but all of these other forces are directed directly into point G, the center. Whoops. Okay. Okay, so what do you think? We have lots of methods in this class. So which one do you think? Should we use equations of motion, like sum of forces and sum of moments? Should I use work energy, or should I use impulse momentum strategies? Why do you say that?
Because you're given forces, you're given acceleration, angular acceleration, so you can do your sum of your moments. Mass moment, inertia, acceleration.
Yes. One extra thing is that it's asking for us to solve for a couple moment. Now, the couple moment could show up in an impulse momentum equation, but impulse momentum requires us to think about changes in angular velocities after some time duration has passed. And it's not asking about some time duration passing, it's asking about instantaneous. And we're given accelerations, not velocity. Right? So we're given an angular acceleration, not an angular velocity. So the fact that it's asking for a couple and it's asking for an angular acceleration tell us that bing, 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 we should be using equations of motion here. Okay. All right. So because it's asking about all of this angular stuff, my first thought is, I wonder if I can get away with just my sum of moments equations. Right? It's not asking about a force, and it's not asking about a linear acceleration. It's asking about angular things, and all the angular things show up in the sum of moments equation. So I'm gonna first off try to write sum of moments about the center point for A, sum of moments about the center point for B. Okay. So for disk A, let's do sum of moments about G for A equals IG alpha A. What are all the things that could be giving me moments? Well, the pin reactions cannot, the weight cannot, the normal cannot. The friction can though. And is that going to cause a positive or a negative moment? Positive, right? The right hand rule. Yeah, so that'll be force of friction times the radius of A, which is half a foot. And then what else? The external moment, right? And is that positive or negative? That's negative, minus M. Equals, I believe these are just disks on an exam. Well, sorry, on the equation sheet, it does tell you it has the mass moment of inertia for a disk. So I'll just tell you for right now, it's 1/2 mr squared. Of course, you have to be able to choose the correct axis of rotation in order to pull out the correct equation, assuming we can do that now. And then alpha A is given in the problem as 4 radians per second. And it's shown in the same direction as that couple. So I actually need to be careful here about that direction. Is that in the positive or the negative k hat direction? The alpha. Angular acceleration. Right. Very good. So this should be -4. All right, mass was 5/32.2. Radius is half. Okay. Alrighty, so what I'm noticing is that I have 2 unknowns in this equation, so crud, I can't solve everything with just the one. If we played around with an idea that would maybe go down an incorrect direction, we could think about, well, like my other equations of motion would be sum of forces in the x, sum of forces in the y equals 0 for A. But we would, if we did sum of forces in the x and the y, we would first of all have to figure out how to decompose force of friction and normal into the x and y directions. And I don't even know if that's possible in this equation, in this setup, because it doesn't even tell us where the pivot points are relative to each other. So I don't even know if if that trig is even possible, let alone it's going to pull in additional unknowns from the AX and then the AY. So I'm feeling really uncomfortable with going that route. So let's go ahead and look at disk B. and some moments about the center for disk B. Okay, let's see. So what all can cause a moment? Well, we already talked about this. There's really only one thing that can cause a moment, and that would be our force of friction times our radius, which is 0.75. And is that going to be a positive or negative moment? Very good. Positive moment. And then mass moment of inertia is 1/2 mr squared. Mass this time is 10/32.2. Radius is 0.75. And we do not know the angular acceleration of B. So, crud. We brought in an extra unknown. So now we have 2 equations and 3 unknowns. So we're still not there yet. All right. However, anytime the problem says without slipping, you need to recognize that it's saying that there's an additional kinematic relationship available to you. And so we need to figure out how to interpret the fact that these 2 things are not slipping with respect to each other. And the way that we do that is probably the trickiest part of that problem that really trip people up. So interpret no slipping. So the trick here is to recognize that we need to use the roll without slip equation so that AG equals alpha R or A equals alpha R. You can think of it as the roll without slip or the fixed axis rotation relationship. They're really quite similar, except roll without slip is talking about the velocity of this, or the velocity or acceleration of the center point, whereas the fixed axis rotation is talking about some point other than the point of rotation. But the rest of it is really quite the same. So I need to use this. So what the heck linear acceleration should I even care about? Like what point on these bodies should I try to describe? Right, the contact point. So what I needed to recognize is that the acceleration of that contact point as related to the motion of disk A has to be the exact same acceleration of that same contact point related to the motion of disk B. Otherwise, they're going to have some relative acceleration, which means that they're slipping, right? Okay, so let's say I have P. I can describe the acceleration of P relative to the motion of disk A by RA, and I can describe the acceleration of, oh, sorry, I wrote 2 A's. Because you're all going to get A's. It's all stuck in my mind. All right, AP relative to disk B is alpha B R B. Right, so I have 2 different relationships that describe the point P, and they need to be the same. So really, I can just put them together, equals alpha B R B. And I want to caution you here that the way that I've currently written it, is a purely scalar, non-directional relationship. And why do I know that? Well, because I know for a fact that A is going to accelerate this way. And if these 2 things are meshed, then B has to accelerate this way. These are opposite directions of each other, right? One is in the negative K direction and the other one is in the positive K direction. So as long as you recognize that the directions are opposite, then this will suffice as long as you interpret that result appropriately. Okay? Otherwise, if you don't want to worry about the directions separately, we could have used the vector version of this, which was AP equals alpha cross r. And the fact that the r's would be in opposite directions would take care of that fact for us. But again, unless we assumed that the r's were, like, we'd have to choose a tilted coordinate system. We could get there. Okay. All right, regardless. All right, so alpha r is, or alpha a is 4, radius is 0.5, alpha b unknown, radius is 0.75. There we go. I can go ahead and solve for alpha b. I will do it with my calculator. 4 times 0.5 divided by 0.75. 2.66 radians per second. And then if I interpret the direction, it's going to be this way, or 2.66 positive k hat radians per second. Either one's fine. Okay, that lets me solve for the force of friction up in our disk B equation. Force of friction lets me solve for my moment in equation 1. Okay, so this is all, at this point, it's just 3 equations, 3 unknowns, solve the system. You want me to continue or? Okay.
Sandra got the answer if you just do the parallel axis theorem using point A. Is that a valid method or is that just chance?
What do you mean parallel axis theorem?
So you solve for, you know that your friction force is your only moment acting on it. So you
On disk A?
on disk A, like only
Okay.
looking at disk A.
Yeah.
So you have your IG of A plus your change from your axis to the outside, which is 0.5, so it's your 1/2 mass of whatever. Like,
Wait, you're summing moments about a point other than the center point?
oh wait, I don't know why it's getting the same answer. Cause that was what.
The
like-
center point is the center of mass. So you really don't need to use parallel axis theorem.
Okay.
Oh, are you wanting to sum about the contact point?
Yeah.
Yeah, your unknown reaction forces would be causing a moment. And your mass would be causing a moment. That would get pretty gross. Because I don't know the moment arm from AX to that contact point, nor do I know it from AY to that contact point,
Okay.
right? Like I don't know this distance. And I don't know this distance. Oop. I'm not given enough information to do the trig there, I don't think.
I don't know, it's
I mean, you
not,
kind of are if you,
Yeah.
because the 2 circles are on, I mean, if you would do a theoretical plane under it, they're sitting in the same thing, so the distance between the center point of A and the center point of B would be like 0.25. So I guess you could, but that would just be,
I mean, no, so my
Yeah.
problem with taking the test was just to do M equals IG alpha. And then after the test, I redid it doing IG plus your distance to the contact point. So it'd be plus like MR squared times alpha.
Oh, okay, yeah, oh, you're right, yeah, you could just use the perpendicular distance as the radius, you're right.
Yeah.
But you wouldn't know the angle that that reaction force works at.
I don't know why it works, but I just know it gets the same exact answer.
Okay.
And I just like, I don't understand how it would. I guess.
Did you ignore the reactions at A?
I just ignored the reaction today, so I straight up just did m equals IG plus my squared and C times alpha
See, that usually works. But it's not working.
to do. No, I don't know why. I don't know why. Like it's like exactly right.
You can just ignore the reaction.
Yeah.
And you didn't take into account the moment caused by weight?
No.
I guess the reaction force would cancel out the moment caused by the weight. The moment of the reaction force. Yes. I guess everything is just perfectly balanced.
So you could draw it tilted so that it was like normal force of friction AX AY MG. That would be equivalent. No, it wouldn't. MG would have to point
Yeah, 'cause
to do your sum of forces. Yeah, some amount of MG would have to point in. But if you don't care about what AX and AY are at all, I'll bet you this is what happened. If you were to solve for what is the value of AX and AY doing sum of forces in the X, sum of forces in the Y, you would not get the correct answer
Okay.
for those reactions. But because you're doing only the moment, it's probably fine. Yeah, I think the math comes out as a wash for the moment part of that equation, but you would not get the forces correct. So overall, you're making a lot of like tiny little mistakes that would affect solving the rest of the dynamics. It just doesn't affect the moments.
Okay.
So it's still extraordinarily bad form.
Okay.
That's what I'm saying.
Yeah. No, I just don't understand why it would still work then because it was like.
It's
But it's just not like same thing as like yesterday when I got the same answer with the wrong method. It's still.
yes, I'm seeing why that's the case now. It's gross, but I can see how it's really just an issue of attributing like an incorrect amount of force to AX versus AY, but it all comes out as a wash for the moments because those altogether the purpose of those forces is to balance everything else that's not causing a moment so that this thing does not go in X or Y. You too, Gio. Don't do it.
Yeah.
Don't ignore reactions. Okay, what else? Whew, half the day.
I have a question about the problem we were doing yesterday.
Which one?
It was 1955. It's the falling bar, the reaction force. Is there a way?
Oh, okay.
Is there a way that you could solve? So in the principal work and energy, the kinetic energy for a rigid body is, I think you've mentioned it briefly, is there a way to solve for, let's say, instead of the G, which was the center of mass, solve it at the end? Because I know you can solve for the moment of inertia at the end.
What do you mean at the end?
At like.
Oh,
point
you
of
mean
contact, so like In this
Yeah.
case, we've been all the way to the right of the bar. I mean, we have a formula for that,
Yeah.
for a slender rod. I was wondering if there was a way of simplifying that so you don't have to
Yes.
find it in the middle and then
Yes.
to the right. And I was wondering if we can do it that way.
So for any body doing fixed axis rotation, the kinetic energy of that body is I about the point of fixed rotation times omega. Right, so this body that we were working with, there was G in the middle and then B at the end. So absolutely the kinetic energy of body BG can either be written as 1/2 mvg plus 1/2 ig omega, or equivalently 1/2 I O. Sorry, these need squares.
Okay. Would there be a way of doing it at point B? Instead of
Not
O?
without using parallel axis theorem. But why would you need to? Omega is the same no matter where you take.
Yeah, but the VG wasn't, so then we had to like go back and
But
solve.
VG doesn't come up if you do the fixed axis rotation version.
But you still need a velocity to do the work and energy when it's gonna hit the.
So the problem is, Giovanni, when we use the conservation of energy equation, potential energy of a rigid body is related to the height of point G. Only.
Okay.
Right? So there was no point solving for velocity of any other point
Yeah, that makes sense.
because we needed that point, right? But we needed to know the velocity of point B coming into and out of the impact, because the impact analysis is very specifically for point B.
Yeah.
Whereas the potential energy is very specifically for point G. So there was no getting around the fact that we were going to have to do some rigid body analysis, kinematics analysis, to relate B and G a couple times.
Thanks.
Yep.
Could you show the setup for question 1 on the practice problem?
Yes.
I just need the freeway diagram, so I didn't keep mixing up the placement of like where the spot is.
Sorry, which problem?
The first word through.
First one. Okay, so you just want to set up your coordinate systems? Okay, then I'll keep it here. So the easiest one to see right off the bat is the r theta, because they've already given you r and they've already given you theta, right? And they've drawn it relative to an origin right here, which I should draw with a better color. So that's our origin. Theta is relative to this horizontal, and my r direction goes straight up to wherever the particle is. Okay. That's fine. So pi over 8 is going to be somewhere less. Let me draw that in green because I always draw paths in green. Something like this. Particle is like right here. regardless, we still keep the same origin and coordinate system. Okay, so I need to recognize that this is the origin. This is theta, which says that my radial direction goes out, u hat r, and my theta goes in the direction of increasing theta, but 90 degrees from u hat r. So something like this. Okay. Then we need to do normal tangential. So tangent is always the easiest because we have the path drawn. We just go tangent to the path. So tangent to the path looks something like this, u hat t. And then normal points into the center of curvature of the path at that point, and is 90 degrees to u hat t. So 90 degrees from u hat t is either down and to the left or up and to the right, but we know we need to point into the curvature. So we need to choose this direction as u hat n. And then for this problem depends on identifying psi. Tell me in words where psi is.
The image are, with your T and your theta. No, R.
You need to look back. It's the positive radial direction to the tangent counterclockwise. Right, so it's this one such that tangent psi equals r over dr d theta. However, if I solve this equation and I get a negative psi, it's telling me the clockwise direction from positive r to the tangent. So one thing that can be difficult is when these systems, when you're drawing them, when these systems appear to be almost overlapped with one another, you want to avoid that at all costs because you cannot assume they are overlapped just because you happen to draw them that way.
Okay, so you end up getting like 21.44 for your side. At least that's what I got.
Uh-huh.
Okay, so that's then clockwise, no, counterclockwise from R to T.
Uh-huh.
The inner direction of the normal. Like normal force from the path.
From the path,
Yeah.
you can choose either direction.
Okay, so it'll work itself out.
Yeah.
If you,
Yep. As long as you only draw one.
Are we expected to memorize the tan psi equals r over dr over theta?
I thought I added it, but I guess I did not. Yeah, you'll just have to memorize it, Samuel.
Well, we do another problem like the one we did in class yesterday with like the rod falling.
With eccentric impact?
Yeah. Or is that like not really?
I haven't given a homework on it and I'm not going to give a homework on it. Homework 11 doesn't even cover it. So
So don't worry.
it's good for you to know because I believe it sets you up well to do orbital mechanics if that were something that you wanted to pursue at like the graduate level. So I want to expose you all to it, but I'm not going to test it on the exam.
For the first problem we did, what was the final answer?
From class?
Yeah, so it was the third problem on the exam too.
Oh, you mean
Yes,
this one? Oh, okay. Yeah, let me find it.
I just want to check to make sure I did it right.
Yep. I just need to look it up. I don't remember it.
I got the same alpha.
It says negative 0.233.
Yeah, the moment is 0.233 in the minus k hat direction.
I don't know how you did that.
There might be a negative issue somewhere. So if we. Okay, so we solved here for alpha B. Oh, sorry. Okay, we solve here for alpha B equals 2.66, but really that needs to be, oh no, that's in the positive direction, sorry.
Under solution guide, you have to negative.
The angular acceleration of A should be negative. How's that? You have that to be positive.
Yeah, sorry. A is negative here. B should be positive here. Yeah, I think I did. There's some, in the solution guide, there's some weird negative stuff going on, like I have a negative here, but
Was it negative 0.156? Is that, or did I misremember?
wait, what? The
For the
final,
final moment.
no, it's 0.233.
It looks like you have your alpha A as positive, so the
The
sign
negatives cancel, yeah. Well, let's go back to the Hibbeler solution. See what we'll do. Test the solution guide. It's for sure 0.233. I just did some funky things with negatives on my solution guide.
Did we not even worry about assigning a
I got 0.233 if you ignore
Based on it.
the moment of inertia.
All right, hold on. I can go ahead and run through it. Zero 0.5 times 10 divided by 32.2 times 0.75 squared. Divided by 0.75. 0.11645 alpha B, which should equal times 2.66.
Yeah, but if it was like on like a surface, the friction force is gonna oppose motion, but for the thing on the right side, for the surface sphere on the right side, it's going with motion.
Yeah, because the friction force is pushing force. Because there's no, like, if you remove the.
That makes sense. Yeah.
If I had the same
Yeah.
question,
That makes sense.
A lot of people, yeah, I heard that from several people that like, oh, friction has to oppose motion. And it doesn't actually.
Mm.
0.5 times 5 divided by 2.2 times 0.5 squared. Times 4. I still get 0.233, Samuel. So you've got to have an algebra error somewhere. There, alpha B in this equation absolutely does need to be a positive 2.66, and alpha A in this equation absolutely needs to be a negative 4. Okay, what else?
I got it, thank you.
Yep. Oh, I was gonna say, today's gonna be our last formal recitation. I'm not gonna have this session next week, but that's because I usually get a flood of people who want like one-on-one office hours based on their new exam schedule for next week. So if you want to meet, we absolutely can. Just email me and we'll set up a time. It's just that everybody's schedule changes this on exam week, so it doesn't make sense.
I did for the redemption, I did fundamental chapter 17, problem 17. And I was just, when I was going through it for the moments. and the-
Fundamental 17. Okay.
So when I was going through it, for the moments, they added on like because I had gotten it for my moments, some of the moments about center of mass, IG alpha. But they have it add, right, they add 200 times the acceleration times 0.4. Or I don't even know what, because I looked in the back of the solution guide when I was checking my answer,
Mhm.
and they were adding that, I don't know where it came from.
And it's not MR squared.
No, because 200 is the mass, and then 0.4 is the radius to the, like, the spool.
Yeah.
Like, I can show you my full work through. Because it's just. I don't really know where it's from.
we can just attempt the problem.
I did that problem as well, I'm pretty sure, so. The friction force is multiplied by 0.6, and tension is multiplied by 0.4,
Mhm.
and there is that 0.2 times 1960 on both sides of the friction force. So it's one multiplied by that value, one multiplied by 0.4, and one multiplied by 0.6, so that becomes the one that shows up in the solution value.
Yeah,
And then they just added over the 200 AG times 0.4 from the other part of the tension. I think it's.
like when you solve tension, when you solve for the x direction, you got T is 200 AG plus 392.4.
I assume that's 0.2 times 9.
Yeah, 1960.
Yep.
And then for the moments equation, did you plug the tension in for that?
So the very first thing I did to solve for the Lewis equation is 450 minus tension times 0.4 minus friction force times 0.6 equals 18.
18 alpha, okay.
And then yeah, because I was confused about that as well. So
Okay, so it just, I think they just plug in the tension during that, okay.
I'm pretty sure they plug in the tension and the friction force, and then they add over the 200. Or they add over the
Yeah.
200, and then they just
They go
Point.
from there.
and then they combine the 2.2 or I guess the 300 value that you have.
Yeah. We can still go through it.
I mean, do you understand it?
Yeah.
Okay.
But the one thing I was confused about with that is in the solution guide, when I just related the linear acceleration and the angular acceleration using the R alpha. They went through the whole equation and like canceled out what was not in the I-hat direction. Do we have to go through, did you have that?
Which R did you use?
The radius from the center to the start of the spool.
Okay, so the 0.4.
Yeah. So can we just, because I had originally written out the equation, A is R times alpha and then plugged in the 0.4, but they went through the whole AG is A, except linear acceleration of A plus alpha cross RG with respect to A minus omega squared RG with respect to A.
Uh-huh.
And they went through and they plugged everything in and then they only took what was in the I-hat direction.
That's strange.
It was weird. Did you?
I did it the way that they did it because I got confused, and I was like, okay, let me just do it how they explained it.
Yeah, like if you go in the solution guide, it like runs through that whole thing.
It really should be AG equals alpha times 0.4.
Yeah, which they get to that eventually, but they go through this whole thing of
It doesn't
canceling out.
say no slip. Is that why?
No, if it had said no slip with respect to the ground, it would have been that AG equals alpha times 0.6. But there is absolutely not a no slip condition,
Yeah, exactly.
but it's being spooled up. It has this inextensible rope that's being spooled up. So whenever you have a spool or like a rope that is wrapping up at exactly the same rate as the circumference of something, you get a quote unquote no slip condition for that particular radius, the one that's being wrapped up. And we've done problems like this before in homework.
So if it was like on a hill,
Yep.
like let's say it had an angle theta,
Uh-huh.
then we would have to use that equation because
No,
no, we could still do the same.
as
thing.
long as you wrote that if you did it to where your acceleration was along the direction of the slope,
Yeah. I mean,
same exact relationship, no change.
okay, yeah, because they had like, they did like normal tangential coordinates.
Yeah, so
Okay.
it's okay. I mean, so you know how sometimes even on a planar problem, I'll use the vector version of the equation to let the cross products handle my directions?
Yeah,
It's like the exact same thing. It's the same way that if you were looking at a body that's doing fixed axis rotation, but you pulled from the equation sheet the equation that relates 2 points on a single rigid body doing general planar motion,
Mhm.
the velocity of the fixed axis point would go to 0.
Yeah.
And you would be left with the fixed axis rotation relationship. So there's like the most general form of these relationships. And then when we talk about these special cases about fixed axis rotation or pure translation or pure rotation, which is fixed axis rotation, you get to simplify those equations to something, right? They're always going to simplify. So I think they just wanted to show that it's, I don't know, they showed some extra work.
Yeah.
It's still appropriate. It's just that you recognize that this relationship was gonna hold because this is a thing that's being spooled out on a rope. And it's fine.
Okay.
Yeah.
That makes sense.
3 minutes.
I just have questions about the, like, broad questions about the redemption. I couldn't find a question that matched, the work through question 2 on the test super well.
Just get the right chapter. I don't care. You're not gonna find any problems that exactly match because that's just not the way dynamics works. So similar was a fairly loose term. I just want you to find something roughly in the same chapter. So if the problem was in particle kinetics, find another particle kinetics problem. If the problem was in rigid body kinetics, find another rigid body kinetics problem. How are we studying for the exam? Homeworks? Okay, good.
Haven't started, but that's.
If you majorly bombed exam 1, you need to look over exam 1 again.
Currently, I'm just still doing the exam 2 redemption.
Currently, that's what you're doing. But that's not
Yes.
all the studying you're gonna do for the final, right?
No, it's not.
Very good.
For the translating, there's a question on the practice final, it's like translating, it's the 2 reference frames one. Where it's like the ant and frisbee, so that's just pretty much just have your equation, just look for all the variables somewhere. And make sure you set your x, y correctly for each one.
Notice I didn't test that this year. There's only so much time in the semester. And I really wanted to get to impulse and momentum this year. So yeah, I'm probably not gonna give you a frisbee and ant problem.
Is the final just 5 multiple choice and then like, or is it more multiple choice?
5, what? I only need 1 minute. I gotta go to the bathroom anyway, so I'm gonna kick these guys out. 5 multiple choice, 5 work through problems.
Okay.
Yep.
Okay, and since we did get to impulse momentum, definitely make sure to look over that homeworks and exam 1.
Except I've already told you that I'm not gonna test eccentric impact of a rigid body.
Right.
Yep. Cool. Study hard.
Thank you, Dr. Higgins.
You're welcome, Samuel. Samuel, I wanted to apologize for
Thank you, Dr. Higgins.
yesterday.
I couldn't hear you, I'm sorry.
I wanted to apologize for my snarky comment about being tired yesterday.
I'm sorry for being curt in response as well.
You're fine. You're fine. All appropriate.
Thank you. I appreciate that.
All right. Good luck. Let me know if you need any help with studying.
Of course. Thank you.
See ya. Bye.
Right, and you said you'll submit, or you'll post the final practice.
I will.